Hey everybody, happy Wednesday. We are ready to review for the final exam next week. Remember that I switched the lecture here so you'd have a little bit of review time here so that when you hit Thursday, things won't, we'll just be focusing on review. I'll be there tomorrow. Don't forget we've got a quiz. Just so you know, the quiz covers, it covers area between curves, volumes using the slice method, and volumes using the shell method. So there's no L'Hopital's rule on that quiz. It's just volumes using both methods and the area between curves. If you guys still have questions, I'm happy to answer those prior to the quiz tomorrow, since I know that you've got a substitute today. Depending on how much we get through today, if we do a little bit of new material, then we can spend all tomorrow just on review problems and going through stuff and seeing if you have questions. If we don't get enough time today, which is totally fine, then I'll do a little bit of new material tomorrow. I do want to go over a few things, so it's important that we do that. All right. So the final exam review. Right, I'm not going to throw a ton of stuff on potentially on this final, but there are a few big ideas from this course that I want to make sure you got. A large portion of your grade will be L'Hopital's rule, areas, and volumes, since that's the stuff that we just most recently did. It's not going to be everything, but some of what you're going to do, some of what you're going to have is on there, okay? So the first kind of big topic that could be on that exam are limits, computing limits. So I'm just going to go back through what were our techniques for computing limits, just so we can remember those. All right? So if you remember, the first thing that we always try to do is we always try to plug in. If plugging in doesn't work, if we have a fraction that's in the form of 0 over 0, really one of the first things you should now try to do is L'Hopital's rule, right? Because you now have a nice rule that fits there. But the other things that we had there before were, just to remind you if you wanted to try to use those instead, were factor and cancel, use conjugates if you have a square root that's sitting there, get a common denominator if you have fractions in fractions, simplify. If you see absolute value, then you look at both sides. You look at the fraction coming from either side. I think that's all that we had for 0 over 0, all right? That's one of our indeterminate forms. One of the other things is if we had a fraction and the top is not going to 0, but the bottom is going to 0, then we know that that's going to be an infinite limit. Sorry, my pen's already dying here. That's going to be an infinite limit. And what we do is we look at each side. That doesn't work. We look at each side. We look at the limit from each side to see if it's positive or negative to help us know if we're going to positive infinity or negative infinity. Okay. All right. If you have a fraction and the top and bottom are going to infinity, again, that's the perfect candidate for L'Hopital's rule. But we also had divide the top and the bottom by the highest power of x on the bottom. Do you remember that? So we had that rule. And finally, we had the squeeze theorem. The thing that I'm going to say about the final exam, if I give you a limit, most of these should be L'Hopital's rule, okay? In other words, you should be able to use L'Hopital's rule. So you should be familiar with L'Hopital's rule. That's the best approach that you have for this. So since we're on the subject of L'Hopital's rule, let's just remind ourselves that you should be familiar with those indeterminate forms. Okay, 0 over 0 or infinity over infinity. That doesn't mean you can't do the limit. That just means that you don't know what it is right away. And then we had these other indeterminate forms, 0 times infinity, infinity minus infinity, and then the power forms. The power forms I will not put on the final exam, okay? That I think I mentioned before, but I just want to reiterate that, all right? So limits were our first big concept. So you should feel comfortable calculating limits. I can't let you escape calculus without feeling comfortable with limits. Second big concept was continuity. Okay, you should know a conceptual definition here. What I mean by that is a continuous function is a function that has no breaks. Okay, you should remember, like if I give you a function and I say, where is this function continuous? You should know, oh, there's a break. Another thing to remember is that if you're continuous at a point, that means both sides, right? So you can't have coming in here and then a filled in point and then doing something else down here. That's not continuous. It has to be both sides. So for example, square root, when you go to 0, that's not continuous at 0 because there is nothing on one of the sides, right? Do you remember that? And then we had talked about kinds of discontinuities. So there were 4 of these, remember? So we had removable, jump, infinite, and oscillating. So for instance, I can give you a graph and I can say, where is this function continuous? Where is it not continuous? What kinds of discontinuities does it have? Okay? So you should feel comfortable with that. All right. The next big topic that we had was on derivatives. So derivatives. All right. And for derivatives, you should understand, again, sorry, my pens are dying here. All right, you should have a conceptual definition of derivatives. In other words, it's the slope of the tangent line. It's also an instantaneous rate of change, right? Remember us talking about that? We went over derivatives enough, that definition, that I want you to know the definition. So at a point, the derivative at a point, f prime of a, is the limit as x goes to a of f of x minus f of a over x minus a. Remember that definition? And then the derivative function, f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x over h. You should know those two definitions. I'm not going to ask you to do a lot with them, potentially, but I do want you to know those definitions. Okay, just like with continuity, how can this fail to be differentiable? Okay, remember there were 3 ways that you can fail to be differentiable. If you're not continuous, if you have a corner, or What's our third way? Remember this? Tell the person next to you, what's that third way to be discontinuous? It's where you have a vertical tangent line, right? All right. And then the big thing that you definitely need to know for derivatives is your derivative rules, which you've been using and using and using and using. So I don't know that you really need to do a lot with that. You need to make sure that you're using the chain rule correctly, that you're using the quotient rule correctly. I can throw some problems on there, just here's a function differentiated. Okay, you should feel comfortable doing that. There are some problems on the review section that are just that. Here's function differentiated. If you don't feel comfortable with that, definitely go through those problems. You definitely should plan on doing those problems. Okay. Okay. So we had limits, continuity, different derivatives. All right. Then one of the applications of derivatives that we went over, you guys did a bunch of homework problems on, but I never actually put on an exam, was sketching curves. And the reason that I like the sketching curves examples is that it incorporates a lot of the stuff that we've done. So more than likely, hint, hint, I'm going to put a curve sketching problem on there. Now, when I do curve sketching, I will give you part A, B, C, D, E, F, G. All right, so, but just as a reminder, the things that you look at are the domain, the intercepts, okay, when x equals 0 and when y equals 0, symmetry, okay, you plug in negative x, and see what happens. Asymptotes, where does this have a vertical asymptote? Where does it have a horizontal asymptote that involves the domain, that involves limits at infinity? And then you look at increasing and decreasing and local maxes and mins through the first derivative, right? Take the first derivative, set it equal to 0. Then you look at concavity and inflection points. And that involves the second derivative. Okay. So I have on the review sheet among the review problems, 2 curve sketching problems. You should take a look at those. I would highly recommend that. We can go over those on Thursday if you'd like to, or other types of things, okay? So curve sketching brings together a lot of nice things about derivatives. Then we got to integrals. Okay, again, a conceptual definition of integrals would, I'd like you to have that. This is the sum of rectangles. It's actually the limit of the sum of rectangles. All right, so we use rectangles to figure out what the area of a non-square region is. You should know your rules. Okay, the overall rules for doing integration. Okay, we've gone over those a lot. You've used those a lot, so I don't know that you really need to do a lot of review there. You can decide for yourself if you feel like you do. And then we had our techniques. This is chapter 7 that we just went over. So those techniques were simplify, substitution, integration by parts, which you should always do last, trig integrals, trig substitution, and partial fractions, right? I'm not going to spend a whole lot of time on this because we did a whole chapter's test on that. But you could expect to get 1, maybe 2 integrals on this exam. Again, I want you to be able to show you're coming out of this class with a good foundation. All right, and then last but not least is the Chapter 6 material. So we have applications of integration which involve areas between curves. Okay, this is section 6.1. And then volumes using the slice method. That's 6.2. And the shell method. All right, 6.3. Okay, there will, like I said before, there will be an emphasis on the exam on those two areas, as well as L'Hopital's rule, which I put, since that's the material that's come since our last exam. But I will put in some things that are overarching ideas of this course that I want to make sure that you're coming out of the course with the knowledge of those things. All right? Make sense? Okay, so we'll make sure we spend some time tomorrow. I'll be there in class. We'll spend some time tomorrow going over these things. What I want to do now is let me go ahead and go through briefly the material on this last section that I wanted us to go over. So I should be able to, given that we've only gone about 15 minutes so far, I should be able to get through this material today. Tomorrow when I'm there in class, we can just focus on review problems and that kind of thing, all right? So we will plan on that then. Let me go through this last, it's actually half of a section here. All right, so this last section is on length, because I mentioned we were going to talk about length. And particularly when you're talking about curved length, we use the term arc length here. All right? So the idea behind what we're about to do here is we've got a function from A to B, but we want to find the length of that curve. Okay, if the curve was straight, if it was a line, we could get the length. But when it's curved, just like with area, it makes it much harder to find length. So what we're going to do, just like we did before, with area, we're going to cut this region up into a bunch of pieces. All right? So you can imagine cutting this function. We've got a bunch of points here. All right? And then if we zoom in, okay, we're going to want to add up. Okay, so we're going to take a sum of the lengths of these. So let's zoom in here. So if I've got these 2 points, and then what we're going to do is instead of using the actual curve, which I don't know how to get the length of, we're going to connect those 2 points with a straight line. Let's see if I can get another. We're going to connect those with a straight line, and we're going to use the length of the straight line to approximate the length of the curve. Right? Now the way that we get the length of the straight line, this way down here, that length is delta x. Right? We make all of these lengths delta x. So this same length is delta x, and we're going to call this height difference delta y. So this straight length right here is going to be, by the Pythagorean theorem, the square root of delta x squared plus delta y squared. Right? So on each of these regions, region 1, 2, 3, 4, all the way up to n, I want, instead of the length of the curve, which I can't get, I'm going to take the length of the straight part, which is the square root of delta x squared plus delta y squared. Right? So that is going to, and then if I let n go to infinity, that's going to give me my length here. Just like when we did rectangles, we found the areas of the rectangles, and then we let n go to infinity. Here, to get the length, I find the lengths of the individual pieces, and then I let n go to infinity. Now, before we let n go to infinity, what I want to do is I'm going to factor this delta x squared out of the integral, out of the square root. So then it's just going to become delta x. All right, sorry, my computer blanked again. Well, let me do an intermittent step here. Let me factor out a delta x squared from this. Now, from the first term, I would just get 1. The second term doesn't have a delta x in it, so what I'm going to do is I'm going to make this delta y squared over delta x squared. And you can see that if I were to multiply this back through, what would be left on that right side is delta y squared. I'm not sure if you can, it may not be big enough. Let me rewrite this so it's a little bigger. Okay, I'm going to factor out a delta x squared, and in the first term I'm just going to get 1 here. But in the second term I need a delta x squared on the bottom, so that if I were to multiply this back out, I would get what I had up there originally. So now let's pull that delta x squared out of the square root, and it just becomes delta x. The square root of delta x squared is just delta x. And I've got 1 plus delta y over delta x quantity squared, right? So what we're going to do now is we're going to let n go to infinity, and if you remember what happens when we do that, the sigma, the sum, sigma is the Greek letter s for sum, becomes a Roman letter s, that's our integral. Okay, and we label where we're going from and to here. The delta x, delta is the Greek letter for d, so that becomes a dx. And this becomes my function here. So in other words, I get, and all those deltas become d's, so I get dy over dx squared. So in other words, this is the derivative. So the formula for arc length, what this does is this gives us the formula for arc length. The way that I get the length of that curve is it's the integral from a to b of 1 plus the derivative squared dx. All right, that's how we're going to get arc length. Again, I'm not putting this on the final exam, but it's good for you to have at least seen this. Okay. So what I'm going to do is run through 4 examples, just so you can see this work in a few different contexts, and then we'll be done for today. And tomorrow we'll just work on review problems. All right? So let's start with this formula and double check it in the case where we're actually using a function where the length, we actually know it. So let's look at a line. Let's particularly look at the line y equals 2x plus 1. And let's go from x equals 0 to x equals 2. Okay? So 2x plus 1. Right, that's the line. And if we were to go from 0 to 2, the length of that line, we should be able to get just from the Pythagorean theorem by saying this is 2. If it goes over 2, it's going to go up 4 because it's got a slope of 2. So this length right here should be the square root of 2 squared plus 4 squared. In other words, it should be the square root of 20, which is 2 root 5. Let's see if our formula gives us that same length. Okay? So our formula would say the length of that function, 2x plus 1, from 0 to 2, what we do is we integrate from 0 to 2, the square root of 1 plus the derivative squared. Now the derivative is 2, so we're just going to take 1 plus the derivative squared, 1 plus 2 squared. So That's the integral from 0 to 2 of the square root of 5. Square root of 5 is just a number, so its integral would be square root of 5x. And when I plug in 2, I get 2 root 5. Yay. That actually works. So in the case where I can actually check the answer, it really did work. All right? So let's try it now in a few cases where we don't know what the actual answer would be. Okay? Now, one thing, in order to make this not a really terrible experience, many times the functions you have to pick to do exercises have to be, they look very contrived, but they end up working out really nicely. Let me give you an example of what I mean by that. All right? Okay, let's take the function x cubed over 6 plus 1 over 2x. And let's go from x equals 1/2 to x equals 2. All right? So I want to know the length of this curve, which I don't know what it looks like, but maybe it's something like that. From 1/2 to 2. And I want the length of that curve from 1/2 to 2. You can see it blows up at x equals 0. All right. Okay, so the length, in order to do the length, we're going to need the derivative. So let's go ahead and do that now. The derivative is going to be, we're going to get 3x squared over 6 plus 1/2. This is x to the minus 1, so when we differentiate, we're going to get negative x to the minus 2. So in other words, we're going to get x squared over 2 minus 1 over 2x squared. All right? So now the length, the arc length, is the integral from 1/2 to 2 of the square root of 1 plus this derivative squared. Okay. Now if I square this out, let's write it out and then we'll FOIL. So x squared over 2 minus 1 over 2x squared, x squared over 2 minus 1 over 2x squared. Right? So if we multiply that out, what we get is x squared, x to the 4th over 4. Right, and these I'm going to get 2 when I do the cross terms, the inner and the outer. I'm going to get 2 of those, so minus 2. X squared over 4x squared plus 1 over 4x to the 4th. So in other words, what I get is 1 plus x to the 4th over 4 minus 1/2 plus 1 over 4x to the 4th. And notice that the 1 and the 1/2 can be combined, and what I get now is x to the 4th over 4 plus 1/2 plus 1 over 4x to the 4th. Now, do you follow what I did there? It's multiplying out. Now, what you're supposed to notice when you do this problem is something very kind of clever, that this and this basically look the same except for that minus sign. What that means, let me just write up our Arclength formula here. What that means is that that thing actually factors the same way the original thing factored, except instead of a minus, it's a plus because of that difference here. So this factors as x squared over 2 plus 1 over 2x squared. X squared over 2 plus 1 over 2x squared. In other words, that thing's squared. And when it's under the square root, that means we can just drop the square root. And I get x squared over 2 plus 1 over 2x squared. You see that? So the way that these are off by a minus sign, which means that this thing and the other thing are just different by that one minus sign there. That means that now we can do this integral. So we've got 1/2 and x cubed over 3 for the integral of x squared, plus 1/2, and the integral of x to the minus 2 is negative x to the minus 1, or 1/2 to 2. So what I've got there is 8/6 minus 1/4. Okay, that's plugging in 2, and then plugging in 1/2 gives me 1 over 48 minus plugging in a half here actually cancels that 2, and I get a minus 1 there. All right? I'm not actually that interested in what that number is. I could compute it, but it just doesn't seem that fun. And well, let's go ahead and do it. Convert everything to 48ths. We've got 64 48ths, 12 48ths, 1 48th, and 48 48ths. So we've got 51 48ths plus 48. So we've got 99 48ths is our length there. Okay. All right, so basically we're just using that formula, and then we have to manipulate the square root. It's that square root that makes this formula very hard to use. You've seen that square roots many times. When we're faced with a square root, we have to do trig substitution, which then gets us a trig integral, which might have us do integration by parts and other stuff. So, I mean, square roots are not fun to have in fractions. Okay, let's look at 2 more examples. We'll be done. Okay, let's take the function natural log of cosine of x. Okay, and that's from x equals 0 to x equals pi over 4. So if we're going to figure out the length of this function, you could graph it in your graphing calculator to see what it looks like. But if we need the length of this function, to get that length, we need the derivative. So let's go ahead and compute the derivative. So the derivative is 1 over cosine times the derivative of cosine, which is negative sine. So in other words, we get negative tangent. So when we find that arc length, so we're going to go from 0 to pi over 4, the square root of 1 plus the derivative squared. So in other words, 1 plus tangent squared. And you can see that this is cooked up such that 1 plus tangent squared is a trig identity that we had. That's secant squared. And the square root of secant squared is just secant on this region. And secant was one of those integrals that I did ask you to memorize. So you should have secant memorized. If you do not have secant memorized, please put that on your review list to take a look at. All right? So the integral of secant is the natural log of secant x plus tangent x. And let's just sub in sines and cosines. So this is 1 over cosine and sine over cosine, if that helps you plug in from 0 to pi over 4. So when I plug in pi over 4, cosine of pi over 4 is root 2 over 2. Sine is root 2 over 2. Minus, when I plug in 0, cosine of 0 is 1. Sine of 0 is 0. And the natural log of 1 is 0. So what I get here is, if I flip this, 2 over root 2 plus 1. In other words, the natural log of root 2 plus 1. Right? That's our length there. The key here, the thing that makes doing this integral awful is the square root, and the key here is recognizing this trig identity that helps you be able to do the integral. Okay? All right, one last example here. Let's do cosh. Okay, from x equals -1 to x equals 1. Or f of x, whatever. So we need the derivative. So the derivative of cosh is sinh. And if we then look at the arc length from -1 to 1, 1 plus the derivative squared, so 1 plus sinh squared. This is another hyperbolic trig identity that we had before. Cosh squared minus sinh squared is 1, just like cosine squared plus sine squared is 1. So cosh squared is 1 plus sinh squared, which is what this was cooked up to do. So I get the square root of cosh squared. Square root of cosh squared is just cosh. And the integral of cosh is sinh. So I need sinh of 1 minus sinh of -1. Sinh, just to remind you here, sinh is e to the 1. Sinh of 1 is e to the 1 minus e to the -1 over 2. Sinh of -1 is e to the -1 minus e to the 1 over 2. If I factor out that half, we've got e minus 1 over e minus 1 over e, and the negative gives me a positive e. So I've got e minus 1 over e. Okay. So that's just to introduce you again to the idea of arc length. Arc length is I've got a curve. If I had a straight length, I can get the length of that using Pythagorean theorem here. When I've got something curved, I have to resort to an integral. And that integral involves a square root, which can often be very nasty. You have to cook up the problems very specifically to make them work out to be doable. So I will not put arc length on the exam, but it's good for you to have at least seen it. Let's spend some time tomorrow going through any questions that you have, any problems you'd like to review, if they're specific, if you want to do some curve sketching, if you want to do some more limits or derivatives or integrals or areas or volumes. If you've got some other homework questions, you can definitely bring those too. We'll spend the time just going over those types of questions. So thanks, and I will see you tomorrow in person. Take care.